I'm going to start with just kind of a little overview of statics, where it falls in engineering classes and stuff, other classes that you'll likely take. And then I'll take questions about homework. I gave you those vector problems to work on. They're still not due until midnight tonight. And you can still turn them in up to tomorrow at midnight, so you still have time to work on them. I think largely the thing that'll be tricky about that is maybe just a new format that you're not used to, but okay. So here's where statics kind of falls in things. This is in the engineering world that we call mechanics. And it basically starts with physics 1. That's not how you spell physics. And then from physics 1, for most people, statics is the next class. So the nice thing about statics is you don't have to worry about accelerations and velocities and stuff. Like everything just goes away in Newton's laws. So when things move in Newton's second law, you just think like, okay, it adds acceleration, but it actually adds a lot of complexity. And, in some cases, that is all it does, is just like you put the acceleration in there and you have a new variable. But in other cases, as you'll see when you take dynamics, like it adds a lot of stuff. So statics is a way to get used to free body diagrams of engineering problems. Get used to using Newton's laws before you get the complexity of all the calculus that comes in and all the vector manipulations and stuff that are sometimes required. From statics, now this is where it branches out. In one side of statics, you go to the question, will it break? The first class that's really kind of devoted to that question is deformable body mechanics. That's what we call it at Normandale. Almost every university in the country calls it, mechanics of materials. Okay, but at the U, they call it deform, so that's why we started calling it deformable body mechanics deform. But if you ever see a mechanics of materials book or a mechanics of materials class, that's what that is. And then from there, most of the time the next class you take is just kind of advanced deform that often is called continuum mechanics. That's a cool name. It brings in a lot more complicated math. And then from there, you can sort of go in two directions. The less practical and more mathematical direction is just keep going with continuum mechanics and it never stops, So that'll keep going as long as you want. On the other side, the most practical one, and really like if the one that you use for complicated deform-related questions about stress and strain, whether you're in research, a research environment or a corporate environment, is finite elements. And finite elements is a computer approach where you just break up the body into a bunch of little pieces and then do like a numerical approach to it, computer approach. There's so many things in the world of engineering that were so cool before people invented computers. And now like all the coolness just became almost overnight, like totally irrelevant. Sad, but it's nice if you don't like complicated math, because for the most part, numerical approaches are just, the math isn't very complicated and it just works so much faster and better than anything else, All these geniuses over the centuries came up with all this continuum mechanics, and then like on Monday morning, they're like, oh, you don't need that anymore, okay.
Wiped out in decades.
Yeah, right, right. At most. Um, on the other side of will it break is how will it move? And dynamics is the first class that talks about that question. So I think of these as kind of parallel. Deform at Normandale, this is engineering 2331. Dynamics is engineering 223. No, 235 is the one we're in. Dynamics is 2236. And at the university, in the mechanical engineering department, I'm pretty sure they now teach this as just a single class. Statics and dynamics are a single class. I think if you major in aerospace engineering, they still do it like this with statics for a full semester and then dynamics for a full semester. But that kind of stuff changes every once in a while. Okay, so this dynamics class uses Newton's laws, the one we teach here, the one that most of you will probably take in the spring. So I'll call this Newtonian. And then after you've taken this, now at this point you would transfer. We don't have any more classes after this. And now you can take a second dynamics class. Let's call it more dynamics. Except this next dynamics class is going to focus on a Lagrangian approach, which incorporates energy into it instead of forces and moments and stuff. So you can think of this as like energy methods. And then from the Normandale dynamics class, you also get a branch here that goes into fluid dynamics. And so statics, deform, and dynamics is the end of what we have at Normandale for mechanical classes. But then this is, and these two, you know, you can keep going forever in these into advanced dynamics and stuff like that. Okay, so you are here. This is a map for you to try to escape from engineering. Anybody have any questions about any of those things that you've always wondered about how these classes go together? Yeah.
How does thermodynamics fit into that?
Yeah, it's kind of on its own separate thing, although since thermodynamics, forces are some of the stuff we'll be talking about in thermodynamics. So thermodynamics is really like a connection between thermal property effects and forces, okay? And so since forces come into it, you could squeeze it in over here into dynamics. And sometimes we'll do that in thermo a little bit, but we won't really emphasize it. But and then obviously like electrical stuff is all over on the other side, but you can use circuits to produce forces and things, and then you can do the dynamics. And it probably a lot of you are taking physics 2 right now, is that right? Or a lot of you have already taken physics 2. So in physics 2, I guess you did some Newton's laws, like talking about accelerations of electrons or whatever in electric fields, you know. So you can kind of combine them, but they're sort of their own thing. Any other questions? Okay, so here are some of the kinds of problems that we're going to do in this class. Probably the heart of statics, if if like a random professor was told like you get one problem, one question to ask people to see if they know statics okay, they would probably all give a similar kind of question, and it would be a connection of rigid bodies. And if you have a connection of rigid bodies connected by joints that doesn't move, it's called a structure. The same thing, but it does move, is called a linkage. But so, for example, a structure would be like hold on a sec. Why did I choose so many members? Okay, but something like this. And we want to calculate the reaction forces between those members. So obviously this has a lot of civil engineering applications and stuff. The same idea, actually, I mean, you use in all sorts of different ways. One is, so in biomechanics, you use this stuff all the time. So here is, oh no, am I making his leg too long? This is a diver. He's modest, he's wearing a bathing suit. He's standing on the platform. Okay, so you can treat like a body as a linkage, a connection of rigid bodies connected by joints, and then you can calculate the forces in the joints, the forces required by the muscles to hold it in static equilibrium. You know, so most of the structures we're going to do are going to look like the one on top, but you can use this approach for a lot of other stuff. So that's what this human body is supposed to represent. And actually, so I have 2 degrees, 2 engineering degrees from the university. The first one was a master's in biomedical engineering, and my research was all in this kind of stuff, accelerations of body segments and stuff like that, forces in muscles, forces in joints, stuff like that. Then the second, so this is structures. And then the second big thing we're going to start talking about is internal loads. And so if you have a beam like this, and you have a force here, and let's see, something like this, and you're applying a force like that, what are the loads applied to the material, not by the outside, but by the adjacent material? And this is the first step in trying to figure out where you're worried about something breaking, how likely it is to break. So this is really like the lead in to deform. Okay. How and where will a fracture start? You know, that's what we're starting to get to with these internal loads. So that's kind of the heart of what statics is, those 2 questions. Anybody have any questions about that? What happened to this guy's forehead or something?
No, that's pretty good drawing.
Yeah, that's what happens to your forehead when you dive from the 10-meter platform. Okay, well, let's get into vectors. So we have a bunch of time. Let me first just start by summarizing a few of the important things, and then we'll have time to answer any questions you have about it. Okay, so in physics 1, when you talked about vectors, you most likely talked about it in a form that's like some number times I plus some number times j plus some number times k, right? You've probably seen that format before. In this class, it's not going to mean anything different, but we're going to represent this as a column vector A, B, C. Okay, so this is the x component or the I component. This is the y component and the z component. And if there, there's a reason why we're going to put it in this new format, and that is that there are a lot of useful matrix manipulations that we can do with vectors. So putting a vector into like a matrix format like this is going to give us a lot of mathematical tools. Okay. In physics, you did a lot of stuff in 2D, and we're going to continue to do a lot of stuff in 2D. So just remember that if you have a vector that's like AI plus BJ, you can write this two ways in this new format. That means this. But then anytime you have third components floating around for your matrix calculations, think of this as equivalent to A, B, 0. Whoops. Okay, so just remember that these are always the same thing. Like if you have two vector components, you can just always treat it as the third one is equal to 0 if it's necessary in your calculation. Okay. To express a vector as coordinates. So let's say that you have so let's say this is the horizontal. And this is 30 degrees. And let's say the length of this is 1.5. And that could be any vector quantity. I didn't put any units on it, but that could be a velocity vector, an acceleration vector. We don't know enough. We just know the number, the length of it. And so what are the vector components first in a coordinate system like this, the one we're used to. And then second, let's say in a coordinate system like this, where this x-axis is 30 degrees from the horizontal. Okay, so in any case, so for any coordinate system, CS's coordinate system, take the counterclockwise angle theta that goes from the positive x-axis to the vector, and it's important that the tail of the vector is moved to the origin of the coordinate system for this to work. And then the coordinates of the vector, so let's call this vector, I'll call this vector u, and the arrow symbol says that it's a vector. And then the components of u are going to be the length of the vector times the cosine of that angle theta, length of the vector times the sine of that angle theta. Okay, so that always works. If you go clockwise instead of counterclockwise, then you just make that a negative angle because it's the opposite direction of rotation. And so for part A, let me draw it again. So we have a coordinate system like this. The tail of our vector goes at the origin. The length is 1.5. This angle is 30 degrees. Okay, so start at the positive x-axis and go counterclockwise until you hit that vector. What's that angle theta? 30, positive 30, yep. Or you could, if it doesn't make much sense, but you could go clockwise and call that negative 330 degrees. And whichever one of those you do, plug it in and you'll get the same answers for the components. So u, in this case, for this coordinate system, is equal to 1.5 times the cosine of positive 30, 1.5 times the sine of positive 30, and you get 1.299, 0.75. Yep.
Are we going to run into any issues with angles over 360?
Nope. It'll keep working. So if you wanted to call that 390, it would still work. But that would be a weird thing to do.
Like a screw, maybe.
Yeah, right. We will not run into any problems with that. Although there are issues like that, and maybe that's, I think maybe you've kind of heard of that before, but it becomes an issue when you have three-dimensional rotations. Three-dimensional rotations make everything complicated, and I'll just leave it at that for now. But it's never going to come up in statics. And then for part B, so now we have our coordinate system like this. Our vector just goes straight along the positive x-axis. So of course you can first just eyeball that and say that's 1.5 in the positive x direction and nothing else. But you can also, this cosine sine thing still works. The counterclockwise angle starting at the positive x-axis and getting to the vector is 0. So this is 1.5 times the cosine of 0, 1.5 times the sine of 0. And so you just get 1.50. Okay, and those are both right. It just, each one is specific to its coordinate system. For entering vector components into your calculators, we're going to be doing a bunch of vector calculations in calculators. So this is specifically for TI calculators. That's what the vast majority of students have. If you have a different one and you want my help figuring out how to enter vectors, let me know and we can figure it out. But TI calculators are so great. The one sort of annoying thing is that so much changes from version to version, And so like the 83 and 84, you have to do so many things totally different than the Inspire or the 89. So here's how to do it on the different types of calculators. So first, if you have an 83 or an 84, I think an 86 also, then what you have to do is go to the matrix environment, which is like a second function, and then math, I think. Do you see where it says matrix on your calculator if you have that type? So you have to go to matrix, and then go to edit. And then you have to, choose the dimensions of your matrix. Since we're going to be dealing with vectors, these are just going to be either 2 by 1 if it's a 2D thing, or 3 by 1 if it's a 3D thing, okay? Because our matrices are going to be, they're going to have one, like the rows are going to have a length of 1, and the column is going to have a length of either 2 or 3. And then once you've put your matrix in there, then you have to exit out of it, and then you can use that matrix in calculations by going back and selecting it. It's a very like clicky kind of way to do it, but it works fine, I think on an 84 and an 86 you can do this, maybe. I know you can do it on an 89 like this. And that is use a square bracket to say that you're entering a matrix, and then use square brackets again for each row in the matrix. So this would be like you'd enter in A, B, C. And then you'd go, you use the store function. I think it is just listed as SDO. And you'd put that in whatever variable you want if you want to save it. On the 89 only, you can use a little quicker syntax that's a square bracket to say that you're entering a matrix, and then go A, semicolon, B, semicolon, C, and then store in whatever you want. And then last, on the Inspire, there is a, so go to the button that looks like, so this button looks like, who designed this button? This is all on one button. That's what the button looks like. And then enter 2 by 1. Well, they actually give you, they show you this or this. And then you can just enter it. Okay. For vector calculations that we're going to need, we are going to need to be able to add vectors, to multiply vectors by numbers, and to multiply vectors by vectors. So the first one is adding 2 vectors. And the meaning of this is if you have A, B, C, plus DEF. The sum of these two vectors is A plus D, B plus E, C plus F. Okay, so if you do it by hand, you can do it that way. If you have these two vectors defined in your calculator, you can just use the regular plus symbol in your calculator, and that's what it'll do. Okay. The second one is multiplying a vector by a scalar. A scalar is just a number, like a vector with a dimension of 1 by 1. So if you have a scalar value D and you're multiplying it to a vector A, B, C, that gives you the vector D times A for the X component, D times B for the Y component, and D times C for the Z component. So you just multiply each component by that scalar. And third, multiplying two vectors. Well, there are two different ways to do this. The first one is called the dot product. And sometimes you'll see it called the scalar product. And sometimes you'll see it called the inner product. It's nice to know these different wordings for the same thing because it's a way to make other people feel stupid, like if they don't know the word you're talking about. It's a useful tool, especially when you get to the University of Minnesota. It'll be nice to have that in your back pocket. Okay, so the dot product so if you're multiplying A, B, C dotted with D, E, F, the answer you get out is not a vector, it's a scalar. And it is A times D plus B times E plus C times F. And so this is why this is called the scalar product. Because the output of this multiplication is a scalar. And the reason it's called the inner product is because it measures kind of like a projection of these two vectors onto each other in a way. So it's measuring how much these two vectors are in the same direction. Okay, so that's what the inner product thing is. And the other calculation that we're going to use a lot, maybe more, I guess, is the cross product. And this one is also called the vector product because the output of this multiplication is a vector. And it's also called the outer product because it measures how close these vectors are to perpendicular, basically, in a way. If you take the cross product of two parallel vectors, you get 0. Okay, if you take the cross product of two perpendicular vectors, the magnitude of the vector you get out is just the product of the two magnitudes of those vectors. Okay, so it measures how close they are to perpendicular. So the definition of this, so if you have ABC and you're crossing it with a vector D, E, F, here's how it goes. It's a little confusing. How many of you have done calculations with these before? Everyone at some point, pretty much, most people. But the way to do it is, okay, so first we're going to calculate the x component. So I'm going to cross out these two. And then I'm going to take, this is where the name cross comes from. I'm going to multiply this times this minus this times this, like taking a determinant. Okay. And so then I'm going to, so for the x component, it's going to be b times f minus c times e. Okay. Then I'm going to do the same thing for the y component, but the y component, you just have to remember that it's negative of everything. You're going to see that in vector and matrix operations all the time. The y component always has this negative sign that the x and y, that the x and z don't. It just comes up all the time. And so this is, cross out these two, and it's this times this minus this times this. So negative of the quantity a times f minus c times d. And then for the z component, cross out these, and it's this times this minus this times this. So we have a times e minus b times d. We're going to use this all the time, and it's probably worth it to program the cross product into your calculator so you don't have to do this every time. In two-dimensional problems, it's not too bad because in 2D, you know, you just have A, B, 0 crossed with D, E, 0. Okay. So what's the x component of this cross product? Cross out this. You got b times 0 minus e times 0. So that's 0. You see that? The y component, cross this out. Again, you have 0 minus 0. And the only non-zero one you have is a times e minus b times d. So we're going to do a lot of 2D problems, and those are not too bad to do by hand. You only have a non-zero z component. Non-zero z component. Yep.
You mentioned in the vector review, and I've seen this before, where the cross product is equal to absolute value of a absolute value sine angle.
Yeah.
What's the meaning of having a vector equal to a scalar?
Oh, that's just the magnitude of the vector is equal to the magnitudes of the lengths of the two vectors multiplied together times the sine of the angle between them. So then you have to figure out the direction separately, which you can do by the right-hand rule, by the way. So the next thing I was going to say is that a really important thing about the cross product is that the output vector is perpendicular to both input vectors. And the direction satisfies the right-hand rule. Okay, so if you have, so let's say that you're taking the cross product of U and V. Okay, so what's the direction of U crossed with V? And let's say that U is, hold on, minor computer crash. Okay, so let's say that this U vector is in the direction this way. Okay, and let's say that the V vector is into the page. Have you ever seen this notation for vectors before, that a vector coming out of the page you draw as a circle with a dot, like you're looking at the point of the arrow, and a vector going into the page has an X, like you're looking at the feathers of an arrow? Okay, so this is going into the page. So here's how the right-hand rule would work. First, have your fingers pointing in the direction of the first vector. Position your hand in such a way that when you curl your fingers can point to the second vector. What happened to the thumb? Okay. Are you with me on that? Do you see what I'm trying to get at there? And if you position your hand in the way where you can go from U to V by curling your fingers like that, your thumb is in the direction of the result vector, the output vector. Okay. So like, for example, let's think about the coordinate axes. Let's say that X is this way, Y is this way, and Z is sort of coming out towards us. Well, then notice that according to the right-hand rule, the Z-axis always has to be the cross product of X, X cross Y, or I cross J, because in order to have your fingers so it can curl from X to Y, your thumb has to be pointing out of the board in the Z direction. Okay, and that is a required property of a coordinate system that's called a right-handed coordinate system, which is every coordinate system you'll use possibly until you start doing crazy chemistry or quantum mechanics. Or I know there are some places where they use left-handed coordinate systems, but I've never done it. So think of this as just a requirement of a coordinate system. In a TI calculator, if you have a TI-89 or an Inspire, there are functions dot and then capital P. And there's another function cross capital P. And they do dot products and cross products for you. And it's already in there. So you're in luck. If you have a different one, I would recommend getting those programs into your calculator. You don't have to do it right away. And probably some practice doing it by hand is good. But eventually, I think you're probably going to want those in there. So it tells you how to do it, I believe, in an appendix to that statics textbook that's posted on D2L. So you can look at that. Or if you just want to come to office hours or whatever, I'd be happy to help you do it. I know people in here have very different familiarity with programming different things or whatever. Any questions about that? Okay, well, there's 4 minutes left. Anybody have any of those homework questions that you'd like me to tell you how to do? Did that sort of made sense or, okay. Then okay, I want to give you 5 things to keep in mind about this. So 5 things to always remember as you deal with vectors and stuff. The first one is remember that y always has to be the weird one. Y is always trying to screw you up. It always has negatives popping in when you don't expect. So look for that, you know, and remember to use it in the cross product. Y always has to be the weird one. It's part of its personality. The cross product output vector is always perpendicular to to both input vectors. I guess you already have this in your notes. Output vector is always perpendicular to both input vectors. Third, the cross product of any 2 parallel vectors is 0. Fourth, a right-handed coordinate system requires that I cross j is equal to k. I cross k is equal to j, right? Nope, it always has to be the weird one, so negative j. And j cross k has to be equal to I. And then last, order matters. Let's say order matters in the cross product. So A crossed with B is equal to negative B crossed with A. Okay, so you can't switch the order. With a dot product, you can switch the order. So let's say, whereas A dotted with B is the same thing as B dotted with A. Okay, any questions about that? So I'll just assign a few more of those vector problems, and then we'll get into some real statics pretty soon.